Okay, I have to be careful when I record these things because sometimes I don't set the mic properly. I have to tell the computer whether to use the sound coming from my headphone or from the computer, and if it comes from the computer, it sounds like I'm in an echo chamber. So that's not good. So I recorded this podcast for 13 minutes and then I have to redo it, but that's okay. You don't have to worry about it, and I'm just telling you because I'm just liking to complain a little bit once in a while. Okay, so next up, after you decided or you somehow thought about climate always changing and it's changing now, and is it real? Why should we worry even if it's not real, right? If climate is always changing, why should we worry? Because it has changed a lot in the past when we were not around, and if it starts changing now that we are here, we have to worry about it. It's a risk, right? So the question next up is to say, somebody asks this person who's there telling you, don't think about climate change as real, it's a hoax, it's a lie. Then you want to be ready with your science, and the next science question is to say, I can surely measure the increasing CO2 in the atmosphere day after day, and I know where that increasing CO2 is coming from. So there are 2 points, right? One, CO2 is increasing, and I have to know who is producing this. So we'll look at some isotopes on how we do this, but if you are young and haven't had enough chemistry to understand it, don't worry about it. You can skip it or listen to it so that in a few years when you get to chemistry class and the teacher starts talking about isotopes, you can say, teacher, I have heard of isotopes and I want to learn more. Okay, so we already talked about CO2 having varied a lot, changing a lot in the past as well. When the dinosaurs were around, CO2 was much higher, and then the ice age came and CO2 kept dropping and dropping in the last 135,000 years when we had the last ice age. And remember, your good science from before says when ice age comes, glaciers go on land and they hide the vegetation, sea ice grows on the ocean, it traps the CO2 in the ocean, and the CO2 in the atmosphere keeps dropping and dropping, and it goes down by about 100 ppm after the glaciation is complete compared to when it was not glaciated. Okay, so start from the last glaciation, which ended 12,000 years ago or so, 10,000 years, and see how the CO2 increased because the glaciers disappeared and released all that CO2. So before industrial revolution, as we saw before, the concentration of CO2 in the atmosphere was 280 ppm. Charles David Keeling came along, started measuring in the 1950s thanks to the advice from his advisor Roger Revelle at the Scripps Institution of Oceanography in La Jolla, California in the US. And we saw that there is a seasonal cycle. When the sun comes to the northern hemisphere and photosynthesis happens, the trees draw down the CO2 and take it away from the atmosphere, so atmospheric CO2 drops, and when sun begins to go south, the leaves fall, photosynthesis slows down, and that CO2 begins to come back out. So we have this up and down every year because of the seasons. And there is another station which has, if you go to the southern hemisphere, there's much less land. If you go further south, there is only ocean. So the season to season changes will be different. But nonetheless, what we said is we can clearly see that the CO2 has been increasing since the 1960s at least. And we used ice cores and tree rings and corals and other paleo proxies, remember paleo proxies, to do some detective work, and said CO2 hasn't been this high for about 4 million years. Okay, so look at that a little bit. So now we said CO2 is inert, it doesn't react very much other than dissolving into the ocean a little bit, and so it goes around and around. So it's stays in the atmosphere for a few centuries, which means you measure it in a few spots and you got a very accurate measurement of what the CO2 is like around the world, and you can measure it precisely, which means you can always measure it 100 different times, you get the same answer. What else needs to happen? If we are burning so much fossil fuel, right, when you burn something, what happens? You use oxygen. Everybody is driving around, flying around, taking trains. I'm using the computer, the energy, the fan is running, and so on and so forth. Everything is energy. Most of the energy right now comes from fossil fuels. If you burn so many things across the planet, what should happen? Oxygen must be decreasing. Remember, we said before, Charles David Keeling's son, Ralph Keeling, is now at the Scripps Institution of Oceanography following his great father's footprints, and he's measuring not only CO2 to continue after his father passed away, he's also measuring oxygen, and he shows from a couple of stations that oxygen also has been dropping, which is consistent with the fact that we are burning so many things and taking up oxygen. Nothing to worry about. As I said before, oxygen is 20% of the atmosphere and we are safe. We are not using up all the oxygen. If we have a hard time breathing, it's because of the pollution and not because oxygen is decreasing. Okay, what else do we need to do? This is where I will add some chemistry about isotopes, and if you don't want to learn, or if you feel scared of listening, and you may jump out of this podcast, but you can listen and just understand as much as you can. So what do we know? We know that plants take up CO2 for photosynthesis and they lock it up, and we said in the past, Silurian, Devonian, or Vechian, when plants emerged on the planet on land, they took up so much CO2 that they cooled the earth and caused maybe a snowball earth episode. And we said when glaciers grow and ice age comes, CO2 decreases. Remember your ice albedo feedback? As glaciers begin to grow, let's say because the energy from the sun changed in the past, then glacier grows, albedo increases, more of the sun's energy is reflected back to space, so you have less and less energy, so further cooling and more glaciers grow and more CO2 is hidden away because glacier is covering the vegetation and the sea ice is covering the oceans during ice ages, and CO2 is getting hidden. If CO2 is decreased, then greenhouse gases are decreased in the atmosphere. Thermal energy can go out more and can again cause cooling. So you have these two feedbacks happening. Now, what's new? We already discussed this. Well, what's new is we say there are isotopes of carbon. Many elements in the periodic table have isotopes, including oxygen that we mentioned before, saying we use different isotopes of oxygen to reconstruct the past temperatures. Okay, so now we are saying carbon also has isotopes. What does it mean? Carbon as an atom is known as carbon because it has 6 protons. Generally it will have 6 neutrons and 6 electrons when it is just a complete atom, but adding a neutron and not changing the number of protons will not change the basic naming of the element. It will still be carbon as long as it has 6 protons. It may have fewer electrons because it is ionized. It may have more protons because naturally there are some carbon atoms which have 6 protons and 6 neutrons. The ordinary carbon, which is very abundant, almost 97%, let's say. Okay, but there are few rare atoms of carbon which have 7 neutrons, so then you have 6 plus 7, so that becomes C13. The ordinary carbon is 6 protons, 6 neutrons, we call it 612. That means when CO2 is formed, there are many molecules of CO2 and there are many molecules of C12O2 and a few atoms of C13O2. Why does this matter? Because plants which are trying to photosynthesize want to use as little energy as possible for capturing CO2 to do photosynthesis. They want to produce energy by doing photosynthesis. They want to produce organic matter, carbohydrates, sugars, whatever we call it, to produce flowers and seeds and grow the trunk and grow tall and live long and so on. So they only take up more and more of the C12 because that takes less energy than taking C13O2. So more and more of the C12O2 is taken up by plants than the C13O2. So if you look at the organic matter in the plant, which has CO2 bound up with water and converted into carbohydrate or sugar, then you compare that CO2 locked in to the atmospheric CO2, then the plant CO2 converted to organic matter has more C13 than or less C13 than the atmosphere, because it is taking more of C12O2 than C13O2. It's called fractionation. When it takes CO2, it is saying, let me take the easy one, which is C12, so let me avoid C13 unless I have no choice. Okay? This is very good because you can then go and see the CO2 in the atmosphere and see, as we come from the pre-industrial period or from the time of Roger Revelle and collect samples, and here we are looking at data from the 1980 onwards, and you look carefully at how much C13 and C12 there is and how it is changing. If you are putting more and more CO2 into the atmosphere by burning coal and petrol and gas, that is organic matter that was old and buried and that is taken out and burned. Organic matter has less and less of C13, so if you keep burning more and more of the organic matter from the past, then the atmosphere is getting new CO2 by burning, but that CO2 has less and less C13 because it is old photosynthesized material. And we can clearly see, they measure the C13 in the atmosphere from 1980 onwards. We see that it is decreasing in the atmospheric CO2, which means the CO2 that's being added to the atmosphere, which we can clearly measure as increasing CO2, can also be shown to be having less and less C13, which means it must be coming from some organic matter from the past. And that is what the fossil fuel burning does. What else do you want? You said oxygen is decreasing as CO2 is increasing, but as CO2 is increasing, which we know for sure, C13 is decreasing in its fraction of the total CO2. This is beautiful. You can even go back longer, not 1980. You can reconstruct using, the ice cores, the corals, the tree rings, whatever other detective work we can do, and show that even if we go back to the time of the Vikings or 900 AD or 900 Common Era, you see that C13 was different than it is today, which is 2000 something here. You can see that it was not changing very rapidly as we came to the Industrial Revolution. We were mostly only doing agriculture. And then we started burning all this fossil fuel for Industrial Revolution, producing things and using things and driving things and consuming things and so on. And C13 has been dropping like a rock in the atmospheric CO2. That means we are adding more and more of the C13 depleted CO2 to the atmosphere. This tells us very clearly that not only are we increasing CO2 in the atmosphere, not only are we decreasing O2 in the atmosphere by burning everything, but we are producing CO2 that is old organic matter because it is less and less in C13. And this, my friends, is the detective work that tells you that in fact we are adding CO2 by burning fossil fuels. So anybody who's trying to fool you now cannot fool you, because you have mastered your isotopes and you are saying, I just don't believe you that CO2 is not coming from us. It is indeed coming from us burning fossil fuels. Okay? So as I said, if you don't understand isotopes, don't worry and just wait till you get to that class. Right now you just imagine that we have ways of scientifically saying CO2 is increasing, and the increasing CO2 is coming from burning fossil fuels. Okay, we'll move forward now with what else are the arguments that we have to worry about when people say climate change is not real and it's just a hoax. Okay, we'll come back and continue the discussion. Hopefully the sound is good and I don't have to redo this. Thank you.